Now, where do recurrence relations come into play in computer science? They occur, for example, when trying to determine the execution time of recursive procedures. There's even some correspondence between recursion and recurrence relations and mathematical induction, though these are two different things. Recursion is a programming technique. A recurrence relation is a way to define, for example, a function or sequence of numbers. A recurrence relation is not directly related to programming. And as I said, mathematical induction is a proof technique that can often be applied if we try to demonstrate a statement that involves a recurrence relation. Later on we will generalize mathematical induction even further to so-called structural induction. Structural induction is a very useful technique to show the correctness of a loop and in turn to show the correctness of an algorithm. So we will start with reviewing a few recursive algorithms. Then we will try to figure out the execution time function of these algorithms. We will see that this results in a recurrence relation. At the end, we will resolve these recurrence relations. The next video will introduce you then to mathematical induction. So let's try to determine the time complexity of the function that recursively removes the elements from a queue and prints them. We measure the runtime of the function in the size of the queue. If the queue is empty, nothing happens. Otherwise, an element is removed, printed, and then the remaining queue is printed in the recursive call. We count the number of steps. If the queue is not empty, there are the conditional statement, the dequeue operation, and the print operation that can be performed in constant time. However, we have a problem when we try to assign the number of steps to the recursive call to print queue. We are actually trying to determine the runtime of that function, so we seem to be going around in circles. But we still can specify an execution time function as follows. We call the execution time function tprint. If the queue is empty, then the function only evaluates the condition in the if statement and then terminates. In other words, if the queue size is 0, then the number of steps is 1. Hence, the execution time function maps 0 to 1. Otherwise, if the size is greater than 0, the function executes 3 steps and then calls print queue itself for the queue, where the size of the queue is now reduced by 1. So if the size n is greater than 0, then tprint of n is equal to 3 plus the time to execute print queue for n-1 elements. Since we do not have that number, we express that number of steps in terms of tprint itself, that is as tprint of n-1. Here's again the specification of the execution time function. This is actually a well-defined function. It is defined by a so-called recurrence relation. The word recurrence refers to the fact that tprint of n uses tprint itself to specify its value. Although this might seem odd, we can calculate all function values. For example, let's say you want to calculate tprint of 3. Then we first check the argument, which is 3. Since 3 is greater than 0, we have to apply the recurrence relation. So tprint of 3 is equal to 3 plus tprint of 3 minus 1, which is 3 plus tprint of 2. Now we have to determine tprint of 2 in order to get the final value of tprint of 3. Tprint of 2 is equal to 3 plus tprint of 2 minus 1, which is 3 plus tprint of 1. Now we need to determine tprint of 1. This way we keep working our way down until we reach tprint of 0, and then finally we get an actual value. So tprint of 1 is equal to 3 plus tprint of 1 minus 1, which is 3 plus tprint of 0. The function specification tells us tprint of 0 is equal to 1. We plug in 1 for tprint of 0. So the final value of tprint of 1 is equal to 4. Now we can work our way backwards. We plug in 4 for tprint of 1 in the previous calculation and get that tprint of 2 is equal to 3 plus 4, which is 7. Then we plug in 7 for tprint of 2 in the calculation of tprint of 3 and get that tprint of 3 is equal to 3 plus 7, which is 10. As we have seen, recurrence relations can be used to define functions. They are also often used to define sequences of values. Consider, for example, a sequence where the numbers keep doubling. If we start at 1, then we get the sequence 1, 2, 4, 8, 16, and so on. If we call the ith number in the sequence a sub I, then this sequence can be defined as follows. The first number is explicitly set to 1, so a sub 1 is 1. All numbers after the first one are calculated by doubling the preceding number, so a sub I is equal to 2 times a sub I minus 1. The recurrence relation can only be used if the subscript is greater than 1. Analogous to recursive procedures, we call the non-recursive part of the definition the base case. The base case might just specify explicitly one value, or might specify several values. Note that the base case is necessary to accurately define the sequence or a function. The second part is the actual recurrence relation. Now we can define the execution time function of a recursive algorithm by a recurrence relation. Recall the recursively defined runtime function tprint. The recurrence relation makes it difficult to determine the growth rate of the function. What we need to do in order to determine the big O notation of that function is to resolve the recurrence relation. That means we need to find a non-recursive form for that function. Unfortunately, there's no method that guarantees you ending up with a non-recursive form. The best way is first to determine the first couple of values and then to look for a pattern. In particular, we need to figure out how the function argument relates to the function value. Let's try to do that for the recursive definition of tprint. We have already calculated a couple of values. Tprint of 0 is 1, tprint of 1 is equal to 4, tprint of 2 is 7, tprint of 3 is 10, tprint of 4 is 13, and so on. Note that if the argument is incremented by 1, then the function value increases by 3. So the function is likely of the form 3 times n plus some constant value. Since 0 is mapped to 1, that constant value would need to be 1. We can verify that this non-recursive form is at least correct for the first couple values. So it seems that tprint of n is equal to 3n plus 1 for all n greater equal 0. If you cannot figure out the non-recursive form, try to recalculate the function values without calculating the final value. For example, tprint of 0 is 1, but now when calculating tprint of 1, keep the result as 3 plus 1. When calculating tprint of 2, then we get 3 plus 3 plus 1, or 2 times 3 plus 1. Tprint of 3 is then 3 plus 3 plus 3 plus 1, and you will notice that we add the 3 times, which happens to be the argument value. Tprint of 4 is 3 plus 3 plus 3 plus 3 plus 1, or 4 times 3 plus 1. Now it is easier to see that tprint of n is equal to 3n plus 1. At least that seems to be the case. We have not proven that it is really the case. Okay, let's put everything together. We can extract a recurrence relation for the runtime function of print q. Resolving the function results in the function tprint of n is equal to 3n plus 1. This function is linear, so the time complexity of print q is O of n. We will later use mathematical induction to prove that the resolvent we extracted from the recurrence relation is indeed correct. Let's go through the same process for another recursive algorithm. Merge sort is a divide and conquer approach to sort an array. Merge sort divides the array into two halves and then sorts each half recursively. In the combined step, the two sorted halves are merged together to become one sorted array. Here's the pseudocode. Recall that low and high mark the lowest and highest index respectively of the subarray. In the base case, the subarray consists of one element only. In that case, the subarray is trivially sorted and nothing needs to be done. But if not, the index in the middle of the subarray is calculated. That step takes constant time. Then the procedure makes two recursive calls to merge sort, each for one half of subarray. Here the problem is again that we don't know how to count the number of steps, since these calls themselves will make recursive calls and so on. But we can say that the number of steps corresponds to the number of steps of merge sort for an array of half the size of the original subarray. The last procedure is linear in the size of the subarray. So let's try to specify an execution time function for merge sort. We name the execution time function tsort. The function value tsort of n is the sum of the number of steps for the three parts divide, conquer, and combine. We said that the divide step is constant since we need only to calculate the index of the element in the middle of the array. The conquer step makes two recursive calls. Here we can describe the number of steps using the execution time function itself. Since merge sort is called twice, and since it is called for an array of half the size, we can express the number of steps as 2 times tsort of n half. Finally, the combined step is linear, so the number of steps is some constant, say b times n. So the recurrence relation for tsort of n is equal to t times tsort of n plus bn plus c for some constants b and c. Now this does not yet correctly specify the function tsort because we omitted the base case of the recursive definition. We will also simplify the function a little bit. What we do is we just use the expression n to represent the number of steps done by the divide and combine step together. Since the two parts together are linear, that is okay. And that's what we then get. Tsort of 1 is equal to 1. This is a base case where the array consists of one element only. Only the check if index low is less than index high is performed in that case. If n is greater than 1, then tsort of n is equal to 2 times tsort of n over 2 plus n. Note that we are a little bit sloppy. If the array size is odd, and so the argument is an odd number, then n over 2 has a fractional part and the function value is not well defined. In fact, the function tsort is only well defined if the argument n is a power of 2, because only then can the array be split continuously into two halves of exactly the same size. So let's assume that n is always a power of 2. Resolving this function is a little bit more difficult than in the case of tprint, but we try anyway. I suggest again to calculate the first couple values. We can plug in only powers of 2 and take some time to trace the following calculations. Now I will rewrite the function values so that you can see the pattern. The resolvent is tsort of 2 to the k is equal to 2 to the k times k plus 1 for all k greater than or equal to 0. Finding these kinds of patterns is a matter of playing around with the numbers. It's a matter of patience, but mostly it's a matter of experience. We can determine now the complexity of merge sort. We started out with a recurrence relation for the runtime function. Then we made an educated guess to determine a non-recursive form of the runtime function. Since we were a little bit sloppy, our runtime function can only be applied if the input size is a power of 2. In that case, the non-recursive form seems to be tsort of 2 to the k equal to 2 to the k times k plus 1 for all k greater 0. I don't like the argument 2 to the k for tsort. I rather use a simple form like just n as an argument. So we replace 2 to the k by n. If 2 to the k is n, then what is k in terms of n? Well, k is then log of n. So we rewrite tsort of 2 to the k as tsort of n is equal to n times log n plus 1. Therefore, the time complexity of merge sort is O of n times log n. Now this is based on the assumption that we resolve tsort of n correctly. We will prove by mathematical induction that the resolvent is indeed correct. In the last example, we have a look at the recursive implementation that calculates the nth Fibonacci number. If the input value is less than or equal to 1, then the function returns 0 or 1 respectively. Otherwise, the function makes two recursive calls, one passing in the value n-1 and the other passing in n-2. You specify the runtime function tfib in terms of the input value. Note that the input value is actually not the same as the input size here. The amount of memory needed to store a value is generally less than the value itself. The execution time function tfib is recursively defined by setting tfib of 0 and tfib of 1 to 1 in the base case. Because if the input value is 0 or 1, then the function executes a constant number of steps only. Otherwise, if n is greater than 1, the number of steps by function Fibonacci of n is equal to the number of steps executed by Fibonacci of n-1 plus the number of steps executed by Fibonacci of n-2. Thus, tfib of n is equal to tfib of n-1 plus tfib of n-2. It is hard, if not impossible, to resolve tfib, but you might see the resemblance in the way the Fibonacci numbers are defined themselves and the function tfib. Essentially, tfib of n corresponds to the n+1's Fibonacci number, so the growth rate of the runtime function is the same as the growth rate of the Fibonacci numbers. It turns out that the growth rate of the Fibonacci numbers is actually exponential. In particular, one can show that tfib of n is greater than 3/2 to the n-2. And guess what? We can use mathematical induction to prove that claim.